Swayam Prabha. Digital India. Educated India.
Okay, so please take a notebook and write. So you see, let us consolidate what we have seen. So you are given a curve capital gamma of S, okay, and where of course S is the arc length parameter, okay, increasing arc length parameter. S is varying over some open interval in a comma b inside the real line, okay, and you are applying a rigid motion m to gamma of S, and you get a new curve which is m circle gamma of S, okay, and this of course here when I write n r to the n, here n is actually 3, okay, and then the claim is that the new curve m circle gamma has the same curvature and torsion functions as the original curve, okay, and we have proved that. So in fact, what we did is you see the rigid motion is broken down, as you know, into a translation and a rotation, okay, which is an oriented rotation, all right, which is a member of the special orthogonal group, okay. It's an orientation preserving linear isometry, okay, or an orientation preserving map which preserves also the dot products, right. So then we did computations and we showed that so this must be instead of G here it should be T, it should be T circle G here. This should be actually M, all right. So here it should be M, okay, and the reason I wrote G was essentially for all these members of the Frauen's-Array frame, T cap, N cap, B cap, and then yeah, so for the Frauen's-Array frame only G comes into the picture, okay, and T does not come into the picture because it's an additive term, and when you go to the Frauen's-Array thing, you see you are so let me see whether I have said that correctly. So T hat yeah, so the point is that when you calculate so if you look at if you calculate the tangent vector of m circle gamma S, okay, basically you are going to do d by ds of m circle gamma of S, okay, and then but this m circle gamma S will become g gamma S plus m0, and when you do this d by ds, this derivative of this m0 term, that's going to go away because m0 is a constant vector, all right. Therefore finally what comes out is only the G. Therefore the moral of the story is that you see when you write out the Frauen's-Array frame, okay, the effect of M is seen only as the effect of G, all right. So that is why I have written it like this here, all right. So and of course the point is that T gamma T cap gamma is gamma dot. So there is a dot there, there is a d by ds, and that's what kills the translation part, okay. So that's why it's only G that is coming here in all these three, okay, but then effectively what you are applying is actually M. So this has to be you have to change this, okay. And anyway we showed that if you apply M, then the new curve M circle gamma is actually unit speed and it has the same curvature and torsion functions as the original curve, okay. Now the of course all these used properties of the isometry, okay, that it preserves dot product, it preserves norms, and if it is an oriented isometry, it in fact even preserves cross products, okay, that is also used. But let us consolidate this and see what does this actually mean. So what is the meaning of this thing? So you see, we start with, you know, we have started with the gamma, okay, gamma of s. Where is this? See, this gamma of s is, you know, so this, so let us write this down. Gamma is from AB into, you know, R3, so it's a space curve, all right. Yes, so that's what I explained yesterday, right? So you just think about it like this. See, you have so I just want to say that if G is a, I mean, if G is just a linear isometry, okay, forget for the moment that is even oriented, or that is orientation preserving. So G is, you take G to be just a linear isometry, okay. Then what does it mean? The matrix of G will be an orthogonal matrix, right? And if you take the linear map defined by that matrix, you will get back G, okay. But see, don't even worry about the matrix of G. You just think of it as, you know, G as a linear isometry. So, you know, G, what will G do? It's a linear isometry, you know, it will preserve dot products, therefore it will preserve norms, okay. So if you give me two vectors V and W, okay, what is V cross W? It is the unique, it is the vector which will be perpendicular to the plane of V and W, okay. So that V, W and V cross W are in a, are right handed, okay. That's the definition. And the magnitude of V cross W is the, you know, magnitude of V into magnitude of W into this modulus of the sine of the angle between V and W. But now you see, mind you, they are all based at the origin, and this plane containing V and W is also passing through the origin. Now you apply this G. See, after all, G is a linear map. So what will happen is that, you know, V will go to GV, W will go to GW, all right, and the plane containing V and W will also go to the plane containing GV and GW, because this is a linear map. And mind you, it is a linear isomorphism, so it will map a line to a line and it will map a plane to a plane, okay. An isomorphism cannot reduce dimension of its the image, okay. If you take a source set with a certain dimension, the image will also be the same dimension. So if you took a line through the origin, the image under a linear isomorphism will again be a line through the origin. And if you take a plane through the origin, the image of this plane under a linear isomorphism will again be a plane through the origin, okay. So this plane containing V and W will be mapped to the plane containing GV and GW, okay. Now just think about it, V and W, their lengths are going to be the same as the respective lengths of GV and GW, because G preserves norms. That is because G preserves dot products, okay. Then look at the angle between V and W. If you call it as theta, then GV and GW also will have the same angle, at least in magnitude. Therefore, you see, what this tells you is that the norm of G cross W and the norm of GV cross GW, they are the same, all right. Now the only thing is about the direction. Now what is the direction of G cross W? It will be perpendicular to the plane of V and W, so that V, W and V cross W form a right-handed system, okay. Now when you apply G, therefore G of V cross W will be again, you see, the it will be again a vector that's perpendicular to GV and GW. That's again because, you see, G preserves dot product, so it preserves angles. So it's an orthogonal transformation, it will preserve orthogonality. So you see, this V cross W is perpendicular to E, V cross W is also perpendicular to W. So if you apply G, GV cross W will be perpendicular to GV, and GV cross W will also be perpendicular to GW, okay. Therefore you see that GV cross W is also in the direction of either GV cross GW or minus of GV cross GW, okay. And the magnitudes are the same. Therefore this calculation tells you that if G was, you know, any, you know, linear isometry, then G of V cross W will be plus or minus GV cross GW, and you will get plus. And by the way, that plus or minus can be written as determinant G, depending on, you will get plus 1 if G is orientation preserving, and you will get minus 1 if G is orientation reversing, okay. So if you had taken a special orthogonal transformation, that is if you had taken a orientation preserving isometry, or what is called as an oriented linear isometry, then you should get plus, and you will get G of V cross W is equal to GV cross GW. Okay, so the point is oriented linear isometry is not only preserve dot products, they will also preserve cross products. Okay, so that was important in computing the torsion for the moved curve and showing that it is equal to the torsion of the original curve. Is that fine? Yeah. So now you see, so let us consolidate what we were doing. See, you started with a gamma. Okay, gamma is gamma of s. Okay, so gamma is unit speed. Okay, s is increasing arc length increasing. Okay, and now once you have this curve, you want to associate to it the curvature and the torsion. So first of all, you associate the curvature, you get k gamma of s. This is the curvature function. Okay, and then I want to associate the tau gamma of s, which is a torsion function. But mind you, what are the assumptions you have to make? For the for the torsion to be defined, the curvature should be never 0. Okay, and the curvature is only magnitude of the curvature for a space curve. There is no sign in the curvature. Okay, therefore this is always if it is not 0, it is always a positive quantity. So therefore what you must understand is that this guy here should be an element of, it is going to be C, it's a continuous function on AB. Curvature is a continuous function. Okay, in fact actually it will be first differentiably continuous. And the reason is the following. See, the curvature, you see, so let me say a few. So let me add a few things here. For the curvature to be defined, what are the conditions? The curve should be regular. Okay, if for a regular curve, only for a regular curve you define the curvature, right? And then, of course, if it is unit speed parameterized, then it is always regular. And that is if and only if you know that. If you have a regular curve, then you can reparameterize it with increasing arc length and it will become unit speed. So anyway, I have assumed it's unit speed. Therefore, I can define curvature, but what is the curvature is the second derivative of the parameterization. The first derivative is the velocity, okay, and its magnitude is the speed, that is supposed to be 1. The second derivative is your curvature, and of course I have to take the magnitude of the second derivative. That means I have to differentiate twice. So for this I need that your gamma is actually in C2AB. I should be able to only this permits me to take gamma double dot of S, and I have to take norm of that, and that is your curvature function. Okay, so for in order to define the curvature function itself, I need gamma to be in C2. It should be twice continuously differentiable. Okay, and mind you, if gamma is in C2, okay, that means the second derivative of gamma is continuous, and the norm of a continuous function is continuous. Therefore, k gamma of s will be continuous. Okay, so you get this. Then I want the other pair is going to be the second member of the pair is the torsion. Now, when do you define a torsion of a curve? The torsion is defined only when the curvature is positive, non-zero, and in this case, of course, the curvature is positive. Okay, only then you define the torsion. So therefore, moral of the story is I need the condition. So let me put the conditions from the right to the left. You see, I want gamma to be in C2AB. Okay, then I want the curvature to be never vanishing, which means it has to be positive. So k gamma of s should be always positive for all s. Okay, all right. So that means what? This function is not just a continuous real valued function on AB. It has to be also positive valued. So what I will do is I will just put CR plus here. So let me just write that. I need CR plus of A comma. So this CR plus means it is a continuous and positive real value, okay. So if that is true, if the curvature is always positive, only then you can define the torsion, okay. So this needs, so to define K gamma, you need gamma to be in C2, and you need that gamma is regular, okay. Anyway, if you start with gamma unit speed, gamma is regular, okay. But you need to also assume gamma is twice differentiable. Remember, curvature is actually the second derivative in disguise. So you need to differentiate twice. So you need second continuously differentiable. And we will always follow this rule that whenever you want some derivative, you better also assume that the derivative is continuous, okay. So now if this the curvature is positive, then I can define the torsion. So this torsion definition of torsion needs that the curvature is always positive, all right. That is the reason why I have to put this condition on the left side. But then what is the torsion? If you think about it, see, the torsion is, torsion actually involves the third derivative, okay. Therefore, I need to differentiate once more. I have to go to the third derivative of gamma. So that means that the curve should be thrice differentiable, and we follow our convention that whenever something is differentiable, it is continuous also. So that means the third derivative for the curve should exist and it should be continuous. So therefore, the moral of the story is that this to define this torsion here, you need gamma to be in C3AB. And mind you, torsion is real valued, it can be positive, negative, 0, there is no restriction. The restriction is only on the curvature to be positive, okay. So therefore, moral of the story is that you have this extra condition that gamma is also in C3AB, okay. So, but if gamma is in C3AB, it means it's thrice continuously differentiable. That means the second derivative of gamma is further differentiable and the derivative is continuous. But you see, the second derivative of gamma is, its magnitude is the, curvature. Therefore, the moral of the story is that the curvature function is actually first continuously differentiable, okay. And the torsion function will be, just continuous real valued function on AB, okay. So this is how you get so you get a map like this. What you are doing is that you have to take the set of all curves like this, okay. You have to put all these conditions, all right. And of course, if you intersect these two, what will happen is that third continuously differentiable functions are contained in second continuously differentiable functions. They are a smaller subset. So finally, you need only this condition: gamma should be in C3. That is the condition you will finally need, and you will need this curvature being always positive through the interval, okay. And gamma should be unit speed, parameterized by increasing arc length. So this is the set on the left side, and for that set, what you are doing is that given any gamma, you are associating it to this pair, which is the curvature and the torsion, okay. So this is basically, we have set up a map, all right. Now, what is it that we have shown? What I have shown is, you take a gamma here on the left side, okay. Then this gamma will get associated to K gamma of S. So let me write it: K gamma of S comma tau gamma of S. You will get the corresponding curvature and torsion functions. Now what you do is, on the left side, you move this by an isometry. You move it by a oriented isometry, namely it's a rigid motion, okay. Yeah, orientation preserving isometry, all right. So if you remember, we analyzed that rigid motions are isometries, but not all isometries are rigid motions, because the important thing about rigid motions is that they also preserve orientation. So therefore, the rigid motions are the same as oriented isometries, or which are also called as direct isometries, okay. So you apply M, then what you will get is, you will get M circle gamma of S. And what have we proved? We have proved that if you take the corresponding K M circle gamma of S and tau M circle gamma of S, we have proved that this is equal to this. We have proved that the the curvature functions and the torsion functions, the corresponding functions are the same. Okay, for M is a rigid motion. Okay, if you move the curve by a rigid motion, then the thing you are associating on the right side, namely the curvature and torsion, that doesn't change. Okay, what does this mean? See, moving a curve by a rigid motion is an equivalence relation. Okay, and what this statement means is that you have not only a map from all such curves, you have actually a map from equivalence classes, rigid motion equivalence classes of such curves to the right side. Okay, so so I will just say I'll say the following thing. Note that rigid motion equivalence is an equivalence relation on the left hand side. That means what? That means, you see, you make the following definition. The definition is, you see, you take, so let me put, I use capital gamma. So you take capital gamma 1, capital gamma 2 on the LHS. Okay, you take two such curves. Okay, but so what does it mean? They are both the unit speed, parameterized by increasing arc length. They are both C3. Okay, and they both have positive curvature. Okay, and what you do is that we say gamma 1 is related to gamma 2. Gamma 1 is related to gamma 2 if there exists M rigid motion such that gamma 2 is M gamma 1, M circle gamma 1. That means I am just saying a curve is related to another curve. The first curve is related to the second curve if you can move the first curve to the second curve by a rigid motion. Okay, that is the relation I am putting. Now the fact is that this is an equivalence relation. Okay, so this then this is an equivalence relation. Okay, what is an equivalence relation? An equivalence relation on a set is, it is a relation on a set. A relation on a set just says when one member of the set is related to another member of the set. Okay, that's what an equivalence relation is. But the point is that if I give you relations like that, okay, suppose the first member is related to the second member, okay, it need not be necessary that the second member is related to the first. Okay, and the relation may itself be so bad that every member may not be even related to itself. Okay, because a relation is just a it's just a relationship. But in an equivalence relation, it's very nice. Every member is necessarily equivalent to itself. This is called reflexivity. Okay, and if one member is related to the other, then by symmetry, what we mean is that the other member taken as a first member is also related to the first member taken as a second member. Okay, that means there is a symmetry in the relationship. Okay, and then there is a third condition called transitivity. If the first member is, say, related to the second one, and the second one is related to the third one, then the first one is related to the third one. So this is called transitivity. A relationship or a relation which has all these three things, reflexivity, symmetry and transitivity, such a thing is called an equivalence relation. Okay, and then once you have an equivalence relation, the beautiful thing is that if you put together, you take any element and put together all the other elements that are related to it, this will partition your set into disjoint equivalence classes. Okay, and these classes will just contain all elements which are equivalent to one another. Okay, and in this way the whole set is partitioned, okay, into equivalence classes. So so let me write that down. This tilde is reflexive. That means gamma is related to gamma for every gamma. We take we can take M to be identity map on R3. The identity is always a rigid motion. and gamma circle identity is just gamma. So you see this gamma is just gamma, I mean identity circle gamma. Which you can also write it as IR3. Okay. So every curve is related to itself. That's reflexivity. Then what about symmetry? Gamma is symmetric. I mean this tilde is symmetric. So if gamma 1 can be moved to gamma 2 by a rigid motion, then you have to show that gamma 2 can be moved to gamma 1 by rigid motion, and obviously you will use the inverse of the rigid motion. So that is also true. So you see, if gamma 1 is related to gamma 2, then gamma 2 is going to be, you know, m circle gamma 1 for some m. Okay. Therefore, you know, now you use this important fact that, you know, all these rigid motions are they form a group. In particular, every rigid motion has a inverse, which is also a rigid motion. And if you recall, that came from linear algebra. Okay, the use of linear algebra. Okay, so the point is that you apply m inverse circle, apply m inverse circle on both sides. Circle is composition. So m inverse circle gamma 2 will be m inverse circle m circle gamma 1. Okay. And the composition of maps is associative, so you will get m inverse circle m circle gamma 1, and m inverse circle m is identity R3 circle gamma 1, and that is simply gamma 1. So so that means what? This means that gamma 2 can be moved to gamma 1 by using m inverse if gamma 1 is moved to gamma 2 by m, then gamma 2 can be moved back to gamma 1 by m inverse. And this crucially uses the fact that the rigid motions, they form a group, and which importantly uses the fact that every rigid motion, the inverse of a rigid motion is a rigid motion, and which essentially says that you need the fact that they are bijective. Okay, that's a critical thing that came from linear algebra, from the rank nullity theorem, if you remember it. Okay, so therefore the moral of the story is, if gamma 1 is related to gamma 2, okay, then so you get gamma 2 is related to gamma 1. So there is symmetry. If one curve is related to if the first curve is related to the second curve, then the second curve is also related to the first curve. That's symmetry. Okay, and then you have transitivity. What is the condition? If A is related to B and B is related to C, then A should be related to C. But this is very, very easy to see. If you start at the first curve, if it is related to the second curve, I can move the first curve by a rigid motion to the second curve. If the second curve is related to the third curve, I can move the second curve to the third curve by another rigid motion. And it's obvious that if I compose both these rigid motions, that will move the first curve to the third curve. And here again I use the fact that a composition of rigid motions is again a rigid motion. Okay, the rigid motions, they form a group. Okay, so it's as simple as that. Gamma 1 related to gamma 2 and gamma 2 related to gamma 3 implies gamma 1 related to gamma 3. That is the transitivity. And gamma 1 related to gamma 2 is the same as saying that gamma 1 you apply m1 and you get gamma 2. Okay, that is gamma 2 is m1 circle gamma 1. Okay, and gamma 2 is related to gamma 3 means gamma 3, so I can move gamma 2 to gamma 3 by an m2, and that means gamma 3 is just m2 circle gamma 2. Okay, and then now you can see that if you look at the right side, gamma 3 is m2 circle gamma 2 from here. Okay, and from here, and then from here your gamma 2 itself is m1 circle gamma 1, so I can plug it in here. I'll get m2 circle m1 circle gamma 1, but by associativity I can write as m2 circle m1 circle gamma 1. And notice that m2 circle m1 is also a rigid motion, So basically what you are getting is gamma 1 simply goes to gamma 3 by m2 circle m1, and m2 circle m1 is also a rigid motion. So therefore if gamma 1 is related to gamma 2 and gamma 2 is related to gamma 3, then gamma 1 is related to gamma 3. So this related to is you can after having proved that this is an equivalence, you can, instead of saying gamma 1 is related to gamma 2, you can simply say that gamma 1 is rigid motion equivalent to gamma 2. So basically what you are saying is that rigid motion is an equivalence. One curve being related to another curve by rigid motion is an equivalence relation. Okay. Now what you do is that once you have an equivalence relation, you can form equivalence classes. Okay. And every curve, what is the equivalence class of an element? It will be all the other elements which are related to it. So you take a curve, then you take all the other curves that are related to it and put it in one subset. That's the equivalence class of that curve. And of course, you know, if you take any curve, it will be in its equivalence class because it is always related to itself by reflexivity. Okay. And if that curve is related to another curve, they both will have the same equivalence class, because any curve related to any of the two related curves, okay, will be related to the other. Okay. That's because of symmetry. Okay. And transitivity if you want. Therefore, moral of the story is that, you know, if you do this business of taking every curve and putting it in a set which contains all the other curves that are equivalent to it, you get what is called the equivalence class. It's called the rigid motion equivalence class of that curve. And these rigid motion equivalence classes will chop your set into pieces. They will be disjoint pieces. Okay. Because if two equivalence classes meet, it means there is one curve which is equivalent to all the curves in one class as well as all the curves in the other class, but then transitivity will tell you that everything is equivalent. Therefore, these two equivalence classes, if they have even one member in common, they have to completely merge. They have to be the same. Which means that if two equivalence classes, if you take any two equivalence classes, they are either equal or they are disjoint. And of course, every curve is in its own equivalence class. Therefore, all these equivalence classes will chop up your set. So that is called the set of equivalence classes of rigid motion equivalent curves. Okay. And if you form that set of equivalence classes, what is this fact telling you? This fact is telling you that whether you take a curve or whether you take anything in its equivalence class, what you get on the right side is the same. That means you have a map actually from the rigid motion equivalence classes of curves to the right side. Okay. And the classification theorem is that this map is bijective. Basically, the rigid motion equivalence classes are completely controlled by the curvature and the torsion. Okay. So I will write this down. Thus, the equivalence classes on the LHS are obtained, and we call them rigid motion equivalence classes of, you know, curves. Okay. So and I'll put some notation now. So this set here that I've written on the left side, okay, these are all essentially what is this set? This interval, open interval AB is fixed, and these functions gamma are given from AB into R3. So you're going to trace out curves. So these are space curves, which are, so the conditions are this S should be the increasing arc length. So it's a unit speed parameterization, and the curvature function is positive always, and the function gamma itself, the parameterization itself should be C3. Okay. So let us give a name for this. I will just call it as, you know, I'll call it as script C, 3 AB and I will put k greater than 0. Okay, so this is the notation I'm going to put. Right. These are all the script C is supposed to mean that all possible C3 maps. Okay, with for which the associated curvatures are positive, and it should be third continuously differentiable. So that is the set on the left side, and that set on that set we have this equivalence relation. So normally if you have a set and you have an equivalence relation, you write the equivalence classes as set mod that equivalence relation. Okay, going modulo an equivalence relation means that you're putting together elements which are related, and that's basically you are only looking at the equivalence classes. So therefore what you are getting is that you are getting C, so this is C3 AB k greater than 0. Okay, this modulo this, that is the this is the set of rigid motion equivalence classes of curves. Okay, you're putting this this tilde there is essentially meaning that this set is supposed to be the set of equivalence classes. And mind you that the way this is defined is, see, there was this original set C3AB k greater than 0. Okay, you give me any gamma here, what you are doing is that there is a surjective map into the equivalence classes. Okay, so I am putting a double arrowhead to say, just to say that it is surjective. Okay, so this gamma will go to this bracket gamma. This bracket gamma is supposed to be the equivalence class of gamma. So this is, so this guy here is the rigid motion equivalence class of capital gamma. And what is this? What is this equivalence class? It's, mind you, you're taking all the curves which are rigid motion equivalent to gamma and considering them all as a single thing, as a single point. So this is the set of all M circle gamma, where M is a rigid motion. I am taking all the curves that are related to gamma by a rigid motion. Okay, and the what you do is that the fact is that this set here, this is actually a disjoint union. Okay, so this is the symbol for disjoint union. It means if you normally put a U, it means it's a union, but two members in the union can intersect, but you use this special symbol which is like an inverted capital pi. That means disjointed union. That means that it is a union, but no two members of the union intersect. So this is disjoint union of of such equivalence classes. Okay, where gamma is of course where gamma is any curve. Okay, so I'll just put, I'll not write anything more. Gamma is actually here. Okay, and mind you, when you write a set like that, okay, when you write this disjoint union, remember that for every class I can choose only one representative. Okay, because if I try to write the equivalence class of M circle gamma, that will be the same as the equivalence class of gamma. Okay, equivalence class of M circle gamma is the same as the equivalence class of gamma. Whenever two curves are related, their equivalence classes are the same. Okay, so here when I write this, when I write a set, okay, and I have written it as disjoint union, I cannot repeat anything. So here I cannot write box gamma and also box square bracket M circle gamma. I cannot put both there, because then it will no longer be disjoint union. So the point is that this, when you put this gamma here in the index, you should choose only one gamma from every equivalence class. Okay, right. So the moral of the story is that basically what you are doing is, see this, there is a little bit of abstraction here. This box gamma, okay, when it is seen here, it is seen as a subset. It's a subset of equivalence classes. But when it is seen in this set of equivalence classes, it's only a single element. This is the ploy to treat all the equivalent curves as if they are represented by a single curve. Okay. You want to treat all of them as the same. All curves which are equivalent to one another, you want to treat them as being represented by a single curve and work with that. That's the idea. All right. Yeah. So as I told you, see this script C3AB subscript k greater than 0 is this set. It is all those gamma unit speed parameterized curves parameterized by increasing arc length, and the function gamma must be 3 times continuously differentiable, and the associated curvature function must be strictly positive. So instead of writing all that, I am just having a convenient notation. I am calling it as script C3. Don't confuse the script C3 with the ordinary C3. Okay, ordinary C3 is for 3 times continuous differentiability. All right, the script C3 is this whole class. Basically, I am just considering all unit speed curves on an open interval which are 3 times continuously differentiable and which have positive curvature functions. Okay, so having done this, see what you can do is now you have a you get a map. You get a map. This map this will be a map into C1 R plus AB cross C naught R AB, and this is just the map. You send the equivalence class of gamma to the curvature of gamma and the torsion of gamma. Okay, and here is what I want to mention, that you see, if you change gamma by m circle gamma, okay, if you change gamma by m circle gamma, then the square bracket gamma will not change, because square bracket m circle gamma is the same as square bracket gamma. Okay, therefore if I started with gamma, the right side goes to this. If I started with m circle gamma, what will happen? If I started with m circle gamma, I will get, it will go to k m circle gamma of s comma tau m circle gamma of s. Okay, but what have we proved? These two are the same. That means that and on the left side, the square bracket gamma and square bracket m circle gamma are the same because they are equivalent. Gamma and m circle gamma are equivalent elements. Therefore, their equivalence classes are actually the same. The point consisting of the equivalence class of gamma, okay, and the other point which consists of the equivalence class of m circle gamma, they are one and the same point when considered as equivalence classes. Okay, and therefore, if you took any curve equivalent to gamma, rigid motion equivalent to gamma, and took its curvature and torsion, the right side will not change. Okay, so what we have actually proved is that there is a map from the rigid motion equivalence classes of curves to this product of this product space of functions. Okay, and this is the starting point. Now, what is the claim? The claim is now this map is bijective. That is the classification theorem. That is, there is a one-to-one correspondence between rigid motion equivalence classes of curves on one side and pairs consisting of positive curvature functions and torsion functions on the other side. What does this mean? Start with a curve on the left side, you get a curvature function and a torsion function. Okay, if you change the curve by rigid motion, you will still get the same curvature function and the same torsion function. That means that this taking curvature and torsion depends only on the equivalence class, does not depend on which particular member of the equivalence class you are starting with. Then we have to prove what is the injectivity. If you take two equivalence classes which are, say, represented by two curves, and suppose they have the same curvature and torsion, we will show that they are equivalent, that we will construct a rigid motion that will move one to the other. That will tell you that this map is injective. Okay, a map is injective if two elements on one side go to the same element, then they have to be the same. If you translate it, what it means is, if you take two equivalence classes represented by two curves, if it turns out that they have the same curvature and torsion, you have to show that one can be moved to the other by a rigid motion. Okay. So that is injectivity. What is surjectivity? Start with a positive C1 function on AB and another continuous function on AB. I can find a curve for which this positive function is the curvature and the other unsigned function is the torsion. So that is surjectivity. And the fact is injectivity and surjectivity both are true, so you get a bijection, and that is a classification theorem. Okay. So what we have to next prove is you have to prove injectivity and you have to prove surjectivity. And the point is that you see even to define this map, to show that if you move the curve by a rigid motion, the curvature and torsion doesn't change, we have used properties of isometries, and we have used the Frohn's-Array relations. That's what you have to understand. Now again, you have to again use the Frohn's-Array relations to get the injectivity and the surjectivity. The new ingredient now is that you will have to use some theory from the existence and uniqueness of solutions of linear homogeneous first order differential equations or systems of such equations. Okay. So what we can do is, so the claim is the above map from script C3AB K positive to C1 R plus AB cross C0 R AB is bijective. Okay, that is which is otherwise also called as a one-to-one correspondence. Okay, and of course one-to-one is the same as injective, and on-to is the same as surjective. Okay, and a one-to-one onto map is called as a one-to-one correspondence. So what it remains to be shown is the following: to prove two things. Injectivity. What is injectivity? Namely, you start with the gamma 1 and you start with the gamma 2 on the left side, equivalence classes. Gamma 1 will go to k gamma 1 of s, tau gamma 1 of s, okay, and gamma 2 will go to k gamma 2 of s, comma tau sub gamma 2 of s. And the injectivity is two elements. If they go to the same element, then these two elements must be equal. So this is equal to this. Okay, this implies that this equal to this. Okay, so if k gamma 1 equal to k gamma 2 and tau gamma 1 equal to tau gamma 2, then square bracket gamma 1 is equal to square bracket gamma 2. What does that mean? That means there exists an M such that gamma 2 is M circle gamma 1. Okay, that is k gamma 1 s is equal to k gamma 2 s, and tau gamma 1 s is equal to tau gamma 2 of s, implies there exists M rigid motion such that gamma 2 is M circle gamma 1. You have to show this. That is injectivity. What is surjectivity? The surjectivity is you start with a pair of functions on the right side. You have to find the curve gamma on the left side, for which these two functions are the respective curvature and torsion functions. So start with capital phi comma capital psi belonging to the right side, which is C1 R plus AB cross C0 R AB. What does it mean? Phi is a first continuously differentiable real valued positive real valued function on AB, and the psi is just a real valued continuous function on AB. Okay, then show there exists gamma on the left side, which is going to be script C3 AB k greater than 0 such that the curvature of gamma is given by capital phi and the torsion of gamma is given by capital psi. This is surjectivity. So you have to prove the injectivity and the surjectivity. Okay, and once you do that, you have a, you have mathematically accurately proved this qualitative statement that space curves are controlled by their curvature and torsion. A curve is completely determined by its curvature and its torsion. Okay, so this is what we have to prove. All right, so I think I will stop here.